Okay, this is Math 1090, Section 2.1, Systems of Linear Equations. Okay, a system of linear equations consists of two or more linear equations made up of two or more variables, such that all equations in the system are considered simultaneously. For example, consider these cost and revenue functions. Okay, so we could think of these functions as relating maybe y. If we call the output of these functions y, then we have two variables in these equations, y and n. Okay, and what we want to do is we want to find the set of all pairs of values, x and y, or y and n in this case, that satisfy both relationships at the same time or simultaneously. So I've drawn an example over here. Here's an example linear system. This is often, and this is how we usually write such a linear system. So I have x plus y equals 70 and 2x plus 5y equals 200. Okay. Now, notice that if I set x equal to 50 and y equal to 20, then those values satisfy the first equation. But also they satisfy the second equation as well, right? Because 2 times 50 is 100 plus 5 times 20 is another 100. 100 plus 100 is 200. So this point, this pair, this coordinate pair, 50, 20, satisfies both equations in the system. So this is the solution to the system. Okay, and the solution to a system is the set of all points which satisfy all the equations simultaneously. Okay. There are 4 methods for solving systems of linear equations that we are going to present in this section. There's the graphical method, substitution method, the addition method, which I call the elimination method. I do use that terminology. And then in later sections in this chapter, we're going to look at matrix algebra methods for solving systems of linear equations. Okay, some more terminology here. A consistent system will have at least one solution. What we're going to see is that a linear system will always have either 0 solutions or no solutions, a single unique solution, or infinitely many solutions. Okay, so the consistent case covers a unique solution and infinitely many solutions. Any system that has at least one solution is consistent. Okay, and I'm going to skip this next definition and go to the one after it. An inconsistent system will have no solutions. Graphically, this occurs when the two lines are parallel and have no points of intersection. Okay. Now, so a linear system is either consistent or inconsistent. It has to be one of those two. And like I said before, a system that has a solution could have a unique solution or infinitely many solutions. You'll never have the case where a system has exactly 2 or 3 or 17 solutions. It will always just be a single unique point or infinitely many points. And in the case of a 2 by 2 system, and that phrasing 2 by 2 refers to 2 equations in 2 unknowns or 2 variables like x and y. Okay, so we always refer, when we talk about an n by n system or a 3 by 4 system, a 3 by 4 system would refer to a system with 3 equations and 4 variables. Okay, we're mostly going to be concerned with 2 by 2 and 3 by 3 systems in this course. Now, going back to the case where we have a consistent system, there's 2 possibilities, right? Unique solution or infinitely many solutions. So an independent system will have only a single solution, and a dependent system will have an infinite number of solutions. So the 2 subcategories of consistent systems are independent and dependent. Okay, and we have some graphical representations of these terms here that we've just defined. You see an independent system is going to be, if we have a 2 by 2 independent system, we'll have two equations. Each equation will correspond with a line, and the solution set will be a single unique point where the two lines cross. Okay, an inconsistent system would have no point, the two lines have to have no points in common. So that would have to be two parallel lines, because two parallel lines never cross. And then another possibility, though, is a dependent system. This is where the two equations, although they may look different, actually represent the same line. They have the same graph. So their graphs coincide, and thus all the points on the line are actually on both lines, and so we have an infinite number of solutions to the system. Okay, so that would be a dependent system. All right, let's move on to the exercise. A small business produces soap and lotion gift baskets. Labor, utilities, and other fixed expenses cost $6,000 a month. Each basket costs $8 to produce and sells for $20. How many baskets does the company need to sell each month to break even? Okay, so we need to come up with the cost function, revenue function, then the profit function, set the profit function equal to 0, and find the quantity at which we first begin to make profit, right? Where we finally cover all our costs with our revenue. So what is the cost function in this case? Well, we remember cost function has two parts, the fixed cost and the variable cost. The fixed costs each month are $6,000, so we could say C of N is equal to 6,000 plus our variable costs. It costs us each $8 to produce each gift basket, so, and if we produce N of them, the cost would be 8N. Okay, revenue. Revenue is simpler. Revenue is just the price we charge for our product or service times the quantity of product or service we provide, which we're using N here to denote the quantity, and we're charging $20 for each gift basket, so we're going and we're assuming we make N of them, so the revenue would be 20 times N. I'm sorry, we don't need to find the profit function here because we're going to solve this system graphically. Okay. So what is the system of equations? Well, let's remember a function has three variables to it typically, or at least two, but sometimes three, right? You have the symbol you use for the input, the symbol you use for the output, and then the name of the relationship that relates those two variables. Here, C, or for cost, is the name that relates the quantity produced with the output. Now, we haven't chosen an output variable. I think we should just keep it simple and choose Y here and write our system as Y equals 6,000 plus 8N. And then we can write our revenue function as simply Y is equal to 20N. And then we often put our equations together with a curly brace to denote we have a system and they're related. Okay. Now, if we look down on this graph, we see that the cost function, notice it has a y-intercept here at 6,000 because their fixed costs are $6,000 per month, and it has a slope of 8, whereas our revenue function, it always is going to go through the origin because you don't make anything until you sell your first product, right? But it has a slope of 20, so, and the two lines meet here at the break-even point, and it looks like the break-even point has coordinates of N is 500 and Y is, that appears to be 10,000, so 500. At a quantity of 500, our revenue and cost are both 10,000. Okay. So since our profit is our revenue minus cost, and they're both 10,000, our profit is 0. Okay, part E, we could have also found the solution to this system of linear equations algebraically by setting the cost equal to the revenue, which is really the same as saying setting your profit equal to 0, because remember, what is profit? Profit is revenue, I'll use N here, revenue minus cost. And when we want to find the break-even point, what do? We set profit equal to 0. But this equation is the same as setting, right? I could just add C of n to both sides of this equation, and I get R of n equals C of n. Okay, so this is one way we can algebraically solve a system of linear equations that involve cost and revenue. So let's see here, our revenue function, let's do this. Our revenue function is 20n. Let's set this equal to our cost function, which is 6,000 plus 8n, and then solve for the n that satisfies this equation. To do so, I subtract 8n from both sides, and I'm left with 12n, not negative 12n, just 12n on the left. And that would be equal to 6,000. And then divide both sides of the equation by 12, and I get n is equal to 6,000 over 12. 6,000, I'm going to do something a little clever here. 6,000 is the same as 60 times 100. And 12 goes into 60, I know 12 goes into 65 times. So n is equal to 5 times 100, or 500. There we go. And that agrees with our graphical solution to the system of equations we did in the previous part. All right. Let's continue on with this graphical exploration of solving systems. Consider the following system of equations and its graph. What is the solution to the system? Well, let's graph these equations and then find where they cross, and that will be our solution point. Okay, but these linear equations are in what we call general form, where we have something, well, almost general form. Usually in general form we would write something like something times x plus something times y equals a constant, but we have the y terms first here. And we'll see, writing your system in general form is advantageous for certain solution methods, but not so much for the graphical solution method, because in the graphical solution method it's easier to graph the equations if we put it into slope-intercept form first. So I'm going to rewrite this system. The first equation, if I subtract x from both sides, it becomes y equals negative x plus 7. The second equation, if I add 2x to both sides of that equation, I get y is equal to 2x plus 1. Okay, so this is an equivalent way of writing the system, but now it's going to be much easier for us to graph the lines that correspond with each equation. So let's do that. Nope, I want the ruler. There we go. So the first equation is a line with a slope of -1 and a y-intercept of 7. So the y-intercept would be right here. There's 7. And we want a line with a slope of -1. That's going to be a 45-degree angle, but there we go. Okay, let's graph the next line. Y y equals 2x plus 1. So this has a y-intercept of 1 here and a slope of 2. So let's see, a slope of 2 means I have to, if I run 1, I rise 2. So maybe that looks about right to me. There we go. Okay, and clearly the point they cross at is right here. And that is the point 2, 5. So the solution is the point in the xy plane 2, 5. How could we be sure that that's correct? How could we be sure that we did this correctly? Well, we could take those values and plug them back into the system, the original system. The original system says y plus x has to equal 7. Well, 5 plus 2 equals 7, so that checks out. What about, can we put these coordinates into the second equation? Well, let's see, set y to 5 and then x to 2, and we get 5 minus 2 times 2, or 5 minus 4. Yep, that indeed is 1, so it checks out. This point does simultaneously satisfy both equations. Okay. We're going to do another method of solution, solving a system by setting the equations equal to each other. Okay, you are looking at getting a plan for sending faxes. Unfortunately, they haven't died out yet, have they? Faxes. Sometimes you still have to send a fax. The first plan charges 21 cents per fax. The second plan charges a monthly fee of $19.95 plus 10 cents per fax. Okay, write the system of equations. So we have two different plans here. I could write this system as functions, right? Cost functions. Let's do it that way. So one way I'll think of it as, we'll use x will be the number of faxes we send each month, and y will be the cost in dollars. Okay, so for the first choice we could write the cost is, and if we use the functional notation, it would maybe be cost of plan 1 as a function of number of faxes sent. Well, this is going to be just 21 cents times the number of faxes sent, so this will be 0.21x. Whereas with the second plan, our total cost will be, we'll call this maybe C sub 2, it's the second plan. So the second plan will be, we have a fixed monthly fee of $19.95, so that will be $19.95 plus 10 cents per fax, so plus 0.10 times x. There we go. There's a perfectly valid way to write a system of equations. Often, though, we'll leave out the this portion here where we name the we give specific names to our functions, right? Okay, how many faxes would you have to send each month for the second plan to be cheaper? Well, one way to solve a system is to set the right-hand side of both equations equal to each other, and when we do that, when I take the function definition for each cost function, set it equal to each other. In other words, I do this: 0.21x equals 19.95 plus 0.10x. And what has happened here? Well, now I have a single equation in just the variable x. We know how to solve that. I subtract 0.1x from both sides of the equation, and I'm left with, let's see, I'm left with 0, so 21 cents minus 10 cents is 11 cents. So 0.11x equals 19.95. Divide both sides by 0.11, and I find that x is equal to 19.95 divided by 0.11. I'm going to use the calculator here. So 19.95 divided by 0.11. Okay. And we find the quantity of faxes, because remember, x is the number of faxes we send each month. So our quantity of faxes, when the costs from the two plans equal each other, is about 181.4. I'll put a little squiggle over there to indicate about equal to 181.4. So in other words, how many faxes would you have to send each month for the second plan to be cheaper? So x has to be greater than or equal to 182. As long as we're sending more than 182 faxes each month, the second plan will be cheaper. Next, solving a system by substitution. So we've looked at the graphical method, setting two equations equal to each other method, and now we're going to look at the substitution method. Okay, we'll look at one more method, elimination. So in this method, what do? You solve one of the two equations for one of the variables in terms of the other, and then you take that expression from step 1 and you substitute it into the second equation for the remaining variable, and then substitute the solution from step 2 onto either of the original equations to find the value of the first variable. Okay, now that's a little bit confusing, I'm sure, but I think an example will make it clearer. Hopefully will. So let's look at this exercise. So we have tickets to the circus cost $25 for children and $50 for adults. All right. On one day, total attendance at the circus is 2,000 and the total ticket sales is 70,000. How many children and how many adults attended on this day? Okay, and it gives us some guidance here. Let C equal the number of children and A equal the number of adults. So we want to use the variables C and A. Alrighty. Okay, now somehow we have two unknowns. We don't know how many children and how many adults attended the circus. So in order to solve for two unknowns, we need two equations. We need a 2-by-2 system. Okay? So we're going to have to, from this word problem, we're going to have to glean out two linear equations that relate C and A. And then when we solve the system, we can solve uniquely for the how many children and how many adults attended the circus. Clearly, this has to be a unique number, right? Okay, there can't be, there is a solution. We know there's a solution ahead of time because this actually happened. Okay, so let's see here. What can we glean from... Oh, I see four numbers: $25 for a child's ticket, $50 for an adult ticket. Total attendance is 2,000, and total ticket sales is 70,000. So somehow we've got to come up with equations for these with these four values. Well, the simplest one I see is that we know how many people attended the circus that day, and it was 2,000. So that's going to be the sum of the number of children and the number of adults. So clearly we have, I'll put the variables in alphabetical order. So I'll say A plus C. I'll go A first. A plus C has to equal 2,000 because there were 2,000 total in attendance that day. Now the other little bit of information we're given is the total ticket sales, 70,000. How would I compute that number, total ticket sales? Well, I multiply the price of an adult ticket times the number of adults that attended, right? Because the price is $50 per adult. So when I multiply $50 per adult times the number of adults, that's going to give me a dollar amount. And then I add that to the amount of revenue from children's ticket sales, and I'll get the total revenue from ticket sales. So let's see. So $50 per adult plus $25 per child, that has to equal $70,000. And we drop units in these equations. Notice that the first equation has units of just tickets, right? Everything is tickets. Whereas the second equation, the units of everything is dollars. That's okay. Your system of equations, not all the equations have to have the same units. Okay, part B, solve the system using the substitution method. Okay, so step one here, what we want to do is solve one of the two equations for one of the variables in terms of the other. What does that mean? Well, it means something like this. I'm going to call this, we'll put a little curly brace there, and I'll call this equation 1, and I'll call this equation 2. And what I'm going to do is I'm going to solve equation 1 for A, right? If I solve it for A, then what do I get? I get A is equal to 2,000 minus C. Okay? Now what I can do is I know what A is equal to in terms of C, and I can plug that into equation 2. That's step 2. Substitute the expression from step 1, that's the thing I've circled, into the second equation and solve for the remaining variable. So I know what A is in equation 2. So I'm going to replace this A in equation 2. I'm going to replace it with 50. Instead of A, I'm going to write in parentheses 2,000 minus C. Now I've got to write in the rest of the equation. 25C equals 70,000. Okay, now what have I done? What do I have now? I have a single equation in a single variable. I can solve this for C. Let's do that. So I need to expand the left-hand side a little bit. 50 times 2,000 is going to be, well, it's going to be 5 times 2,000 times 10, right? Because 50 is 5 times 10. 5 times 2,000 is 10,000, and then 10 times 10,000 is 100,000. So I get 100,000 minus 50C plus 25C equals 70,000. Let's see, I can combine the C expressions together into negative 25C, and I get, okay, so I get negative 25C, and I'm going to subtract 100,000 from both sides. 70,000 minus 100,000 is negative 30,000. So I get C is equal to negative 30,000 divided by negative 25. Okay, oh, I have a calculator very handy here. This is the same as 30,000 divided by 25, so let's compute that on the calculator. 30,000 divided by 25. Did I get enough zeros in there? Yes. It's 1,200. All right. Okay, so now I've finished step 2. Okay, so this was step 1 right here. Okay. All this work was step 2 of the method. And finally, step 3 is what? Substitute the solution from step 2 into either of the original equations to find the value of the variable, if possible. You won't always be able to solve a linear system, right? Sometimes there's no solution. So what I want to do is I want to take this value for C, and since equation 1 is simpler than equation 2, I'm going to plug that value in for C, the number of children's tickets, and solve for A. So I'll just do a little arrow here to indicate I'm going to do I get here we go, A plus 1,200 equals 2,000. Okay, subtract 1,200 from both sides of the equation and I get A equals 800. Alrighty, so there were 800 adult tickets sold and 1,200 children's tickets sold. Yeah, clearly those two numbers satisfy equation 1. If you want to be doubly sure that your solution is correct, you should also plug it into the other equation and make sure that those values for A and C do satisfy the second equation. They do in this case. All right. Another exercise. Solve the following system of equations via the substitution method. All right. Let's see here. I'm going to solve the first equation for x. So this first equation is equivalent to saying x is equal to 2y minus 23. And I obtain that equation by just adding 2y to both sides of the equation. Okay, now that I have an expression for x in terms of y, I can plug that expression into the second equation for x. I want to replace x with this. So I'm going to get 3 times 2y minus 23 plus y equals negative 13. Okay, let's simplify that left-hand side, and we get 6y. 3 times negative 23 is going to be 60 plus 9, so negative 69. Let's see, I think I will combine the two y terms into 7y, and I will add 69 to both sides of the equation, and then the right hand side becomes 69 minus 13, which is 56. So I get 7y equals 56, divide both sides by 7, and I get y equals 8. Okay, once I've defined one of the values of my solution set, I like to box it. Okay, now I've completed, so this was step right here, this was step 1, this was step 2, and now step 3 of the substitution method is I take this value for y and I substitute it into either equation, does not matter, take your pick. Let's put it into equation 2. So equation 2 is 3x plus y equals negative 13. Thus, we have 3x plus our value for y, which is 8. So 3x plus 8 equals negative 13. And again, just like before, like in step 2, I got an equation with just one variable in it, but this time the variable is x. I subtract 8 from both sides. Let's see. 13 plus 8 would be 21. So I have negative 21 on the right-hand side. Divide both sides by 3, and I get x is equal to negative 7. Okay, let's check maybe by plugging these two values into the first equation to make sure they satisfy the equation. When I plug those two numbers into the first equation, I get negative 7 minus 2 times 8. Is this equal to negative 23? Let's see, negative 7 minus 16. Yeah, 16 plus 7. Yep, 23. Checks out. Okay, to be sure, I've seen this happen before. Sometimes you can have a solution, you make a mistake, and it will, even though you made a mistake, it will satisfy one of the equations but not the other. So really we need to check both. Let's do that. Let's plug in our values for x and y into the first equation, and we get, let's see, so this is equation 2. Let's check equation 1. So we need x minus 2y. Oh, sorry, I'm saying that wrong, didn't I? We did check equation 1. Yeah. We checked equation 1 already. Let's check equation 2. So we plug in 3 times negative 7 plus y is equal to 8. So 8, is this equal to negative 13? Well, 3 times negative 7 is negative 21. Negative 21 plus 8, yep, that equals negative 13. Checks out. Okay, so we know our solution is valid.